We are standing right here on the oldest rocks in the Ottawa area. These are metamorphic rocks, and you'll see as we were talking about in class the other day, you'll see this characteristic texture of very high-grade metamorphic rocks. This is a gneiss that we're standing on. And so the characteristic of gneiss then is that it's banded. It has layers of quartz and feldspar-rich minerals, or bands that are rich in quartz and feldspar, and bands that are rich in biotite and amphibole. Now, in addition to that, when you stand back and you look at this outcrop, this is the first thing you should always do when you're in a new area, is stand back and look at it. You don't want to put your nose right up to it. And the first thing you notice is that there's a whole schoolyard. All of the rock outcrops are nice and smooth and rounded. So are all the rock outcrops on the roadway on the way in. Can anybody say why these are all rounded like this? Weathering, yes. Glaciers, that's right. We're looking at one of the, in addition to this being the oldest rock in the Ottawa area, we're also looking at the youngest feature in the Ottawa area, and that is this glacial smoothing or polishing. These are called roches moutonnées. French term. Almost all the glacial terms for glacial landforms come from the French Alps, where they were first described. And so this smooth texture that we see here on the rocks is the result of glacial ice moving over it, smoothing it off. So there's a neat contrast, the oldest rock, but the youngest geological feature. There are several things that you're going to want to do here. First of all, you're going to want to generally describe what the rock is like. In addition, this metamorphic rock is cut by a number of younger rocks. These are dikes, and if you remember, everybody remember what the definition of a dike is? What is it? It's an intrusion. What's the attitude of the intrusion? Roughly vertical. Okay, so there are actually three types of dikes here, and I'm going to show you the first one. The first one are these pink ribbons that you see running through the outcrop right along here. These are the aplite dikes. Aplite is not a term that we've talked about in class before. Aplite is simply a fine-grained, quartz, feldspar-rich intrusion. And it doesn't have to be a dike. Aplite is just a textural term, actually, meaning fine-grained quartz and feldspar intrusion. Now, several of the interesting features of these aplite dikes are, remember we said dikes were nice and straight, go in a nice straight line? Well, one of the first things you ought to do is just walk along this outcrop and see, is that true? Do these dikes go in a nice straight line? And do they stay nicely confined within some borders? And the neat thing about these aplite dikes is they don't. If you come up and you walk along this dike, you'll see that it zigs and it zags as it goes along this outcrop. In addition, you can find places such as this right here, where part of the dike has actually been injected and then deformed into the metamorphic rock. Okay? So this tells you something about the timing of when this dike came into the metamorphic rock. There are two other sets of dikes. If you walk over this way, there's a large mafic dike. Unlike this one, if we were to break it open, we would see it's made up mostly of pyroxene and feldspar. So it's high in magnesium and iron. One of the things you want to do is contrast that dike, which is maybe about 6 inches wide or so, with this dike. Are the characteristics the same? Then there's a third set of dikes called pegmatite dikes, and I'll just tell you right now, the key thing about the pegmatite dikes is that they are not very big, they're narrow, but they have another mineral in them that's purple. And one of the things that we want you to do by about an hour and 10 minutes or so from now is to decide what mineral that might be. It is a mineral you have not seen in the lab, but it is in your lab manual. It's in your mineral identification list. So you should be able to track it down with a little bit of help. And those dikes are located sort of where there's a bit of a little valley running between the two big roches moutonnées just behind over here. This is a beautiful example of the Aplite dike. Notice, it has the characteristics of a dike. If you can just stand back just a little bit, has a sharp edge, and you can see that the dike, here's the foliation in the metamorphic rock, oriented this way on both sides. And you see that this cuts right across it. So, everyone who's in class, we've already talked about cross-cutting relationships. The CUTV students haven't seen that yet, but this is a beautiful example of a cross-cutting relationship. So right away, you know that this must be younger than that. Has to be, okay? But there's also these interesting little things. You'll see that, notice there's these little injections of dike here into the metamorphic rock. And the interesting thing is, here's another one. There was another one right there. Notice that those injections are parallel to the foliation. So, and also notice that this, even though this is a nice edge, I mean, this is a very, when you look at it right there, you can see there's a very sharp contact between the dike and the metamorphic rock. But if you follow the dike, you see that it squiggles, it gets thin, it gets thick, it has these injections here. That suggests that this dike came in while this was still very hot. And so this dike has been deformed, not as much as the metamorphic rock has, but it has a little bit. This was, I call this soupy. It must have been pretty plastic when this came in, and then this stayed hot and was able to deform a little bit after it came in. You still have the nice sharp contact that tells you it's a dike, but it has been deformed, very definitely. And I would say that it happened while this metamorphic rock was still buried very deeply, and it was still very plastic.
The pink's potassium feldspar?
That's right. That's one of the things. Potassium feldspar, if you go back to the minerals part of the lectures, can have a variety of colors. But when you see a pink igneous mineral, you can make a pretty good guess that it's probably potassium feldspar. So these Aplite dikes, very rich in K feldspar with a little bit of quartz, so they're pink. Now, contrast that. You'll notice that also there's a lot of light-colored things in the gneiss. And if you scratch this with your knife, you should be able to figure out what it is. I won't tell you right away. The neat thing about a mafic dike, remember, a dike is an intrusion. It's coming up into pre-existing rocks. When we were looking at the Aplite dike back there, remember that the edge where the Aplite dike was in contact with the metamorphic rock was really nice and sharp, okay? Same thing here, right? Nice sharp contract. Here we have the foliation in the metamorphic rock going that way, and we have our dike going off this way. So you know right away then that the dike is younger than the metamorphic rock. Question is, how much younger? Now, the interesting thing is that we have an Aplite dike coming through here. And you see how its orientation is quite different from the mafic dike. And unfortunately, things have gotten very squirrely. But if you follow the mafic dike down through here, it actually thins out and disappears. It ends right there. Then there is this little zone through here where the Aplite dike is strung through and then appears back down here and gets really fat. At the same time, the mafic dike reappears, and you can follow it here going off like so. So this is the only place in this area where the Aplite and the mafic dike are actually exposed in the same spot. And the funny thing is, we stand here and argue which cuts which, because you can't tell. Because here, this Aplite comes through, but the mafic dike isn't there. There's a little sort of a shear zone that runs through here that you can follow right underneath Charles's feet, actually, and goes to where those boudins are, those lozenges that are all smeared out and curving in that direction. So one of the things that here, you don't really find a spot where the Aplite cuts the mafic dike or where the mafic dike cuts the Aplite. But what is really different is the characteristics of the mafic dike. So if we just get down on your hands and knees, if you were to describe physically what this dike looks like, what things do you see? It's really cracked, okay? And how about the edges of the dike? Do you see anything on the edges of the dike, a physical thing? Is the dike perfectly flat? No? What's it got on its edges? Yeah, along the sides that you're stepping on there? Yeah, it's got lichen too. That's too bad. That's just showed up in the last year or so, unfortunately. That's really young. These ridges, right on the edges, you notice the bumps? You follow the dike out. Notice that that's not just a bump. You actually notice that there's actually a bump all the way along the edge, right? This is what we call the chilled margin. And it's what you get whenever you bring a mafic intrusion up into a much colder rock. What do you think happens when you bring this magma up into the cold rock? What happens along the edges? Cools really fast, that's right. Whereas the stuff in the middle stays hot or may even continue to flow. But the stuff on the edges cools really quickly. So the grain size is finer along the edge than it is in the middle. And if we were to actually bring a rock hammer with us and bang off pieces of this, we would be able to see that. The finer grain rock weathers a little bit less than the coarser grain rock does. So you get a really nice record of the chilled margin with this little ridge that you find on both sides. And so that's the giveaway. It's possible that a rock could have a ridge in it, but to have ridges along both edges like that, you know right away that that is a feature that is a result of chilling of this against this.
I just scratched it with a nail.
Scratch what?
I scratched this dark mineral that we don't know with the nail, and it scratches. So mine's beautiful. What's mine's for a nail? It's in my book.
What is what for what?
Yeah, well, it's one of them.
Yeah. Somebody get that cigarette pack out of there. Thank you.
It looks like it's in. You want to take a look? I'm not sure what it looks like. It looks like it's in little flakes. And I'll look at the back.
See, I wish I could turn upside down.
Is there crystals in it?
Huh?
Is there crystals in it?
Yeah, it looks like I can't really see it that well, but it looks like
What number is the nail?
the nail. Oh, it's sorry.
That's not mine. That's okay.
The nail's ninth blade, so 5.6. It's
The nail should be this up.
So remember, it's dark.
it's not really metallic, so it means it's vitreous of some sort.
Where is it?
It's in a pegmatite vein. What's in a pegmatite vein? What's this?
Here we have a really nice example of cross-cutting relationships. It's beautiful. We already know, here we have our mafic dike. We can see here is the metamorphic foliation like this. It's very clear that the mafic dike is cross-cutting the metamorphic foliation, so therefore mafic dike definitely younger. Now we have these little dikes right here. There's only two places actually around here where you can really find a nice example, and this is the best one. Here we have another dike coming through, and here it meets the mafic dike, and it cuts across the mafic dike. So what does that tell you? That's right. This little dike, these little dikes, the ones that are oriented this way, okay, are younger than the mafic dike. Now, the question is, what kind of a dike is this? Is this a pegmatite dike or is this an aplite dike? It's a pegmatite dike. And the giveaway for the pegmatite dikes is, first of all, they are all oriented across the outcrops like this, whereas most of the aplites tend to kind of run at almost right angles to it. Not quite. The aplite dikes are very soupy and highly deformed. Notice that these are very linear. Now this dike shows one of the characteristics of dikes. I was just explaining back at the last outcrop that all dikes are injections of magma along planar zones of weakness. So you can't think of a dike as a point coming up. You have to think of it as a planar batch of magma coming up. And those fractures that the magma is coming up are going to be oriented at 90 degrees to stress direction. So rocks are being pulled that way and that way to open up a fracture. And the magma comes up. Here's a very nice example of how this rock must have been fairly cold when this came up, because this is really fairly linear. Now, dikes commonly don't follow just one little plane. There can be little offsets and little zigs and zags. But the trend of the dike will always be in one direction. And the other thing, you know this is a pegmatite dike. This is the diagnostic thing about the pegmatite dike, is this purple mineral that you find in the center of it. Some of the better spots to look at it were right here. And if you follow this dike out, there are other examples where you see nice clots of purple mineral in the middle. It's got quartz and feldspar in it, and it's got the purple mineral. And I'm not going to tell you what the purple mineral is. As I told you, it's in your mineral ID tables, 2 pegmatite dikes. And so one comes in like this and it dies out right there, but another fracture takes its place that begins right here and then runs along. So these 2 little pegmatite dikes have the same orientation, and they're probably the exact same dike. They're just offset along here. It's just the way that solid rocks break. They never break along one single fracture. They'll break along a number of parallel fractures, and then the magma just comes up along those parallel fractures, as you can see here. But this is the best place to see our mystery mineral. Our mystery purple-black mineral, beautifully exposed here. There's lots of nice crystals. So if anybody hasn't seen the mystery mineral, this is the place to see it.
Dikes are cutting through dikes, so you've got the pre-existing rock, as a Precambrian rock, is then being cut by as a mafic or as a dark-colored dike, which in turn is being cut by as a felsic or as a lighter-colored dike. So you can start to piece a story about how these things form. You've got the pre-existing rock first, is being cut by as a mafic dike second, and that in turn is being cut by a lighter or a more felsic-colored dike here. And how you start to tell as a relative time is as a mafic dike, as it cuts through the rock, as opposed to as a lighter colored dike is cutting through the darker color. So you can start to tell as a relative age based on what is cutting what, or based on the stuff that we saw in the lab, and how when dikes start to cut each other, and then tell the relative age of it.
This one should be 1:1.
Yeah, so you've got the pre-existing rock being there first and foremost, and as a mafic dike being as a secondary event, and then as a lighter colored material being sort of a tertiary or a third event.
Sorry, can you answer his question again? That was good.
Yeah, so you've got the pre-existing rock here first. It's being cut by as a mafic colored dike, which in turn is being cut by it's a lighter colored dike. So you have as a dike going this way is being cut by something like this, and you can see the crack of the lighter is cutting through the darker. So as you know that the lighter colored dike is younger than the darker colored dike. So yeah.
Can anybody tell me why you would think that this originally might have been a sedimentary rock? Because there's layering. That's right. Good answer. That's, if you've got a choice, the precursor might have been igneous or it might have been sedimentary. The fact that we have nice layering in this rock, we have the dark layers and the light layers, suggests that this probably was sedimentary. 4 minerals. Can anybody name 4 minerals that we saw? Let's start with just one. Quartz. Number 2. Yeah, number 3. Biotite amphibole. Number 4. Garnet. How about number 5? Tourmaline. Did everybody get that the dark colored mineral in the pegmatite dikes was tourmaline? If you, especially just down here, 2 very nice little pegmatite dikes, and if you look carefully in the centers of them, they have some very nice coarse grained blackish purple grains. They're elongate. They're shaped like my finger, so they're prismatic. And if you look at them in cross section, there's a couple of nice examples. It has a triangular cross section. So those 2 physical characteristics of the mineral grains plus the color is a giveaway. All right, the order of dike injection. What's the oldest? Aplite. What's the next? Mafic. Last one? That's right. So I hope everybody saw the nice pegmatite dike crossing the mafic dike down here. Can't miss that. Down there, it's a little squirrely. There is a dike cross-cutting it, and if you hunt around and look around, you'll find it's got pegmatite in it. It's got tourmaline in it, but you have to hunt. Okay, did any deformation occur after the mafic dike was intruded? Yes or no? Yes. How do you know? That's right. There's a couple of places where the dike is offset, but it's not by faulting, it's shearing, which means that this country rock was still soft and soupy when that happened. So we're still hot. Not as hot as the aplite time, the aplite dike injection time, but we're still hot. Everybody saw and mapped out how the mafic dike crosses all the outcrops really nicely? Okay, so now, everybody noticed the garnet, but did anybody notice the holes in the rock around here? Yeah. Can anybody tell me what the holes are from? It's from the garnet weathering out. So there's a lot of places down here around where we were looking at the pegmatite dike. I mean, half the rock is holes. And there's other spots around here where half the layers are holes. Those are garnets that have been weathered out. And it's because garnet's not very stable up here at Earth's surface conditions. It wants to be at 20 kilometers depth and 500 degrees Celsius, and it's not that here. So it's a beautiful example of how a mineral that is not stable under these conditions weathers out very quickly. The quartz, the feldspar, the biotite, the amphibole are more stable at the Earth's surface than the garnet is. So the garnet preferentially wears out and leaves the holes. So does anybody have any questions? Is everybody cold? Yes. All right. We are looking at the Nepean sandstone. And this is the unit that is laid down immediately on top of the metamorphic rocks that we saw in the schoolyard. Now, the Nepean sandstone is not really well exposed around here. It is in the center of the Queensway, a little further down, and here is pretty much it. So, obvious thing about this rock, can you tell that it's a sedimentary rock? It's bedded, beautifully bedded. And is it deformed? No, because the beds are still flat. Okay. But that's now one of the first things that I'm going to get you to look at, is, are these beds really flat? And I'm going to ask you, when we split up here in a couple of seconds, first thing you should do is, once again, step back and take a look at the outcrop as a whole. Take in the big scale things first. Are the layers perfectly flat? Is what I'm sitting on perfectly flat? Are all the layers nice and parallel to one another? Then you'll want to think about, okay, what's this rock made of? So you'll want to find yourself a piece. There's some loose pieces sitting up on top here. What are the components in this sedimentary rock? What are the minerals? What's the cement? Those kinds of things. Start by standing back, looking, and then come up, take a look at some of the details. And we'll do this for about half an hour or so, and then we'll get together and talk about what you've seen. We're standing at a rock outcrop just at the entrance to Canada, looking at the Nepean sandstone, which is the youngest of the sedimentary units that were deposited here on top of the metamorphic rocks that we saw at the Canada schoolyard. Now, one of the things you're always interested in is how were the particles deposited to form this sandstone? And one of the clues is right here on this surface. This is an excellent example of what we call ripples. You can see lines of sand here that form a little highs and then little troughs in between. And if you ever go to the beach and take a look at the sand underneath shallow water, you'll see it has the same effect, just little troughs like this. So here's a line of troughs, a line of highs, a line of troughs, a line of highs. So the ripples are oriented this way, and ripples form at right angles or 90 degrees to the direction in which they were moving. So these were deposited by moving water. The water was moving in this direction, perhaps back and forth like this, so we might be looking at a beach environment here, producing these little ripples, which are preserved on the bedding planes, on the flat surfaces in between different sand units. So, beautiful example then of ripples, which tells us then that this sandstone was deposited in water. See those little vertical cavities there? And there's a few more here. So those are little organisms that filter feed. They've got little fronds. Yeah, they burrow from the top down, and then they secrete mucus to keep the sides of the walls from collapsing in on them. And so they just sit down in here, and they have their little filter feeders sticking up in the water, and they get whatever fine-grained stuff for food they collect out of the water, and then they just recede back in. And so they'll live, this unit must have been there, that must have been a water sediment surface for a fair while for organisms to be able to burrow in and make a home there, because if you had a constant flow of sediment coming in, there's no way that an animal could do that. It would just keep getting buried all the time. So this surface here must have been at a water surface for quite a period of time. So those are the burrows, and as far as I have seen, this is the only place along this whole outcrop where you see them. So it was not a very common thing. Yeah, too turbulent. You know, the material here is all sand size. It's not quiet enough. Guys like this really like muddy, quieter water environments where there's not much stuff coming over them, and it's much easier for them to filter feed in quiet water than it is in really rushing water, which this probably was. So it's a tough life. Okay. So one of the characteristics of these sandstones is if you take a look, each of these cracks here represents a bedding plane. That is, each of these is one depositional unit. And then between depositional units, you get periods where you're not getting something deposited. So here, they're maybe 2 centimeters, 4 centimeters. This one's maybe 6 centimeters thick. And you'll notice that the bedding planes are fairly parallel to one another. It's all fairly flat line. And that, in general, characterizes most of the thin units here. But, for example, if you take a look at this unit behind me, here's the bedding plane. You'll notice that the bedding plane curves up quite significantly right here. And this little unit right here underneath it thickens to be several centimeters thick underneath it. And you can just see it very nicely. So what happened was there was a unit here and this is all of it that's left, this little thin bit. And a large water current probably came in and scoured out the top and made sort of a U-shaped scour that was then filled by this unit. So now the base of this unit sits on the top of the erosional surface of the unit that's underneath. So, and you can just walk down this outcrop, you can see that all the thin units are nice and fairly parallel, but if you follow some of these bigger units, you see that their thickness increases and decreases. And in fact, this one, as you can see, if you were to follow this out, thins out to almost nothing further down, and if you follow it out just over to where people are, just over there, it also thins out to almost nothing. So this is just a lens of sediment that is filling a scour in the underlying unit. The surface that the sediments were being laid down on was never perfectly flat. It was always roughly flat. Even this is still roughly flat. Everything here is still horizontal, but the bedding planes aren't perfectly horizontal. And this is sort of an example when I say sedimentary rocks are laid down in horizontal layers. This is a classic example, is that yeah, on a very large scale, that's true. But when you look at individual beds, there are slight deviations from that. And it tells you a lot about what was going on. It tells you that sediment was being deposited, then it was being eroded away, then new sediment was being deposited, and then further down it was being eroded away. Very dynamic. So, if you all turn to page G of your handout, you have a stratigraphic column. And shows from bottom to top all of the rocks that you find in the Ottawa area. So we started out at stop number 1 at the very bottom of the stratigraphic column. That's a rule for stratigraphic columns. Oldest rocks on the bottom, youngest rocks on the top. So we started out looking at the Precambrian rocks, the schoolyard. We then at stop number 2 looked at the Nepean sandstone, which lies immediately above those metamorphic rocks. We're now at stop number 3, the Bob Cajun Formation. We are now in a sequence primarily of limestones and shales, or mudstones as we've been calling them in lecture, that overlie the Nepean sandstone. And this is a beautiful example of a limestone. Limestones are deposited at the bottom of shallow oceans, usually in warm water. Quite often you find a lot of fossils in with limestones, and certainly if you look around the outcrop over here and just down here, you'll see plenty of fossils. Are the layers horizontal? Do the layers dip? Are these layers deformed? What kind of materials make up the rocks that you see here? Do we see differences in textures from layer to layer? Now at the Nepean sandstone, all the layers were quartz sandstone. The layers here are, in many cases, different as you go from bottom to top. So let's take the next 45 minutes. You have your list of things that you're supposed to be looking at. And it's a little wet here, but it's nowhere near as bad as it was when Charles and I were here on Wednesday. It looks like it's a little drier down here. Be careful. If you there's a lot of things to see at the top of the outcrops, so go ahead and climb up, but please, please be very careful when you're climbing down. That's when people tend to get hurt.
Just about to test for if it's a carbonate-based rock, a limestone-based rock. So as you put some weak acid, it should start to bubble. And there, if I put some acid on, that's weakly bubbly. But if I put acid on this, it starts to bubble quite vigorously. And what that tells you is that there's carbonate inside the rock, as opposed to sandstone-based rock, like the rocks that we saw in as the second stop. If I put the same acid on that rock, chances are it would not bubble, because the stuff inside is sandstone-based, as opposed to the stuff in this rock is more of a carbonate-based. So you got the quick and dirty test to tell a limestone from a sandstone is if you put some acid on it. If one bubbles, it's a limestone. If it doesn't, it's a sandstone.
Put an acid on it.
So here we have a sequence of fairly thin-bedded limestones. And we can see, if we look carefully, that we have a coarse grain layer down here with a fine grain layer over that, and then a very coarse grain and fossil-rich layer over the top of that. Then we have a whole sequence, a number. It's about 7 or 8 of these fine grain limestone layers, all of which have these brown tops. That's how you can tell where the top is. Then we have another one of these coarse grain layers on top here. Each of these coarse grain layers probably represents a storm deposit. It's all deposited at one time, probably within a day or maybe even only 2 or 3 days. We see lots of fossils that have been agitated up from other places and all have collected in this one spot, probably because this was just where there was a bit of a shallow where stuff could settle out. We also have between the limestone layers some very, very thin mud layers, which tend to behave what we call recessively. In other words, as they weather, the mudstone layers weather further in than the limestone is. The limestone is a little bit more resistant. So these fine-grained mud layers are telling us that we did have rivers nearby, far enough away that we don't get sand or anything coming out, but we are getting, probably again during big storms or floods off the river, some fine-grained mud-sized silicate particles that are coming out into the shallow ocean and then are being slowly deposited to form these muddy layers. You've got it. The brown layer is oxidation. Now what does that mean?
Well, basically oxygen rusted it.
Yeah, but if we're below water, right, that means the rock's not in contact with free oxygen. So if the brown layer is oxidized, what does that mean?
That the top was on top of water?
That's right. That periodically the top here came out and got into contact with air.
Okay. Oh,
So
the sea level probably rose.
that's right, level is going up and down. This may even be to some extent tidal. Just if we're in an area with really big tides, maybe we're looking at tide being out for a while. But it takes too long to deposit these layers. So it's probably not just tidal. Probably means we're looking at long-term fluctuations of sea level here, so that we would deposit for a while and then this would be exposed to air. And that would oxidize it, and then it would go back underwater again. We'd get some more deposition of limestone, then it'd be exposed back up to air again. I wasn't going to say anything about that until somebody pointed it out.
Okay.
Now this has all been this has all undergone lithification and has turned into a sedimentary rock. Now, oxygen can't react with the rock anymore. Once it turns into a rock, you really slow down that reaction rate between oxygen and particles.
So it could happen, but over a long, long time.
Very long time. Yeah. Make sense?
Yeah.
Okay. This here it's a muddy layer within the limestone, or we'd call it a shale is what we would call it. And the muddy layer represents silicate, very fine-grained silicate material coming out from a river, probably far away from here, but during a flood event, a lot of fine-grained sediment can be carried quite a long distance out into the ocean. And so we're getting layers of this mud deposited between layers of limestone deposition. So, and limestone doesn't like to be deposited where there's a lot of silicate material around. So if the water was really turbid and cloudy during this period of time, limestone wouldn't deposit. And instead you'd get this layer of mud.
What are all those stripes? striations on there.
Okay, now all of this that we're looking at here is what we call hummocky cross stratification. And we saw cross bedding at the Nepean sandstone, where all the foresets, the fronts of the dunes, were all going the same way. Here we can actually see the entire sort of bottom of the dune being preserved in these layers. It's more like it's undulous, like this, as opposed to being just the foresets. So the whole dune gets preserved. We get a nice example here of a scour down where these cross strata here are being cut by this new set that's depositing all these layers that we see right in here. And I was saying that this is how you can always tell way up in sedimentary rocks, is because here we have the truncation and the layers that are over it parallel to that truncation, and the ones underneath are the ones being truncated. So those ones will always be on the bottom, these ones will always be on the top, so therefore way up is that way. But if we were in a region where this whole area had been deformed and perhaps this sequence of limestones had been turned over, this sequence would be upside down, and we would see then, oh, well, this is saying that way up is that way, but what that means is that in fact the rocks have been overturned. So that's how you would make your interpretation. We've got lots of nice fossil beds here. There's lots of nice crinoids. Crinoid stems form these little donuts. And in fact, if you see it, crinoids still exist today on the modern ocean, and they look a lot like this. They have a stem with a flower at the top. The stem is made up of all these rings that go together. When the animal dies, the rings all fall apart, and that's where you get these little donut shapes. The flower is too fragile. It never survives being moved around and agitated in these kinds of environments, so you only preserve the bits and pieces of the stems. There's also mollusk shells around here. And once again, you can see this alternation between fine grain, which still has the cross stratification in it, and the coarse grain layers, which still has some cross stratification in it. So waves were moving back and forth here, really agitating these sediments quite a bit, regardless of whether they're coarse grained or fine grained. So this is a little bit different from further up the outcrop, where it seemed like only the coarse grain and the fine grain layers didn't show a lot of evidence for the grains being agitated around. Here they do. So it's really important when you're looking at outcrops like this to walk around a lot, take a look around a lot. You see a lot of different things.
Do I see crystals in here too? Like,
Yes, this is so coarse grained that there's actually, you can see right by my thumb there, lots of nice calcite crystals. Then on top of that we have some modern things. These planar features that we see here are joints. There's two sets of them, and they're normally at around 90 degrees to one another, and they form simply as the weight of the overlying rock here was removed. The underlying rock then, as it's exposed at the surface, expands, and as it expands it cracks, and these cracks like this and like this are joints that form just as a result of the expansion. So these big long vertical surfaces we see are joints. And if you walk up and down the outcrop, all these joints, this one and this one, it acts like a zigzag pattern. This one, there'll be a whole bunch more parallel to it further down, and as you go down here, there's a lot more parallel to it also. As you're walking down here, do people notice, especially as you're walking from that direction here, there's a dramatic change where there's a slight tilt to all these rocks. These rocks are actually deposited above the rocks down there. Everything is tilting that way very slowly. So as you walk in this direction, you are going up through the stratigraphy. Here we get almost everything here is hummocky cross stratified. Almost everything down there just has parallel laminations. So no evidence of being right at wave base down there, whereas here, lots of evidence they were at it. The other thing is when you're down there, did everybody see that the tops of the beds were a yellow-brown color? Did anybody try to figure out what that yellow-brown color might mean? Can anybody yell at me? Hang on. Anybody know what that means? Sorry? Oxidation. When you get that brown color at the top of the limestone, it means that it was exposed to air and it got oxidized. And in fact, there is one spot down there where there's mud cracks in one of the brown layers. Again, telling you that occasionally the surfaces down there which are exposed down, further up the outcrop, were exposed to air. Here we don't see that. So one of the things you might guess is that as I'm going up through my section here, my water depth is maybe getting a little deeper, and I'm not getting as exposed to air as much as I was earlier on. Okay, before we head home, I just want to kind of bring everything together and put the 3 stops together and work through what has happened in the Ottawa area over the last 2 billion years. And we can do that. We have the power. Okay, first stop. We were at the Canada School. Think about the rocks that you saw there. And let's think about what geological events must have occurred to produce the sequence of rocks. So what is the very first thing that must have occurred? Sorry, deposition? Yes. Remember that we're looking at metamorphic rocks there. And it had to have a protolith, an original rock. And we thought that that original rock was probably sedimentary. So the first thing that happened before the metamorphism is we had deposition of sediments. Okay, what happened next? Sorry? That's right, burial and lithification. It turned into sedimentary rocks. What happened next? That's right, metamorphism. We buried this to such a great depth that our rock now undergoes all these metamorphic changes, turns into a gneiss, undergoes all the deformation, gets folded. What happened next? Igneous activity, yeah. What type of activity occurred first? The aplite dike, that's right, the aplite dike, first igneous activity. What was next? The mafic dike, okay. What happened between the mafic dikes and the pegmatites? Cooling, that's right. So we must have been removing a lot of the overlying rock at this point, because we see significant cooling. Remember, the pegmatite dikes were nice straight dikes. So it infers that our rock had become close to being brittle. So then we had the pegmatite dikes come through. Okay, so what happened next? Erosion. Lots of it. Remember, that metamorphic rock has garnet in it. So that means it was down at, say, 15, 20 kilometers depth when that garnet formed. You had to remove 20 kilometers of rock to expose that at the surface. Okay? It's a lot of rock. You had to get rid of it. Because what happens next? Stop number 2. Well, we must have had our sandstone deposited on top of our metamorphic rocks, right? Because we have the Nepean sandstone sitting on top of the metamorphic rocks. So those metamorphic rocks were exposed at the surface when the sands that form the Nepean sandstone were deposited. So that's why I said we had to remove 20 kilometers of rock, because that metamorphic rock was actually at the surface. Okay, so we deposited the Nepean sandstone. Then what happened? Then we deposited limestones, this whole thick sequence of limestones that we're in. There's also some shales that are in here, some mudstones as well. So then we got all this deposition of sediments. Well, what happened next? Because we know there's a whole bunch of limestones in the Ottawa area that aren't exposed here, but do depositionally sit on top of this. So that all had to be removed before we could stand here. And then, of course, the glaciers had to come by, as we talked about at the Canada schoolyard, to remove some rock and leave our nice, and unfortunately not polished surface, but this surface up here is probably a glacial surface that we're looking at right here. And there's some other spots around town where you can actually find glacial striae on the top surface of these roadside outcrops to show you that the glaciers did indeed run right over this. And so the glaciers took away some things. They also deposited glacial deposits around here, glacial sands and some gravels and things that we use for construction materials. And then, of course, here we are.